Hey guys, sorry this is late. This is the last video for the last problem, number 3 in homework in tutorial 8. It's the truss problem. I wasn't able to make it to lecture on Friday, so I don't know if the professor gave you any shortcuts for this. So the method I'm going to use is just what I got out of the book, because I haven't actually covered influence lines before. But anyway, it's a pretty straightforward method. It's just a lot of algebra, a little bit of geometry. And as long as there's a lot of shortcuts you can use, and if you use those, you should be able to do this problem fairly quickly. This problem is probably the longest one on the homework, so just something to keep in mind. I think the other problems we could do in like about 5-10 minutes. Yeah, and it's just this last one that takes a while. So, let's see. The first thing you want to do is you want to get a very good diagram. Well, I'm gonna draw a crappy diagram because I already know what the answer should be. But and note that I'm just gonna use method of cuts. This is a truss. You have method of sections and method of cuts. I'm just gonna use method of sections and method of joints. I'm just gonna use method of sections here, because if you notice, all your things happen to line up very nicely on this one cut. So you don't actually need to do too much analysis. This is this. I'm not gonna. Well, I'll call this. I'll just call this R. This is force AB, AD, and CD. The first thing you want to do is just drop your unit load. What happens if the problem specifies that you're going to be moving a unit load across the base, across the bottom chord. So as usual, you always want to start off with the reaction. When you have a point load here, do you guys agree that you have no forces anywhere else in the member? Like if I have a point load here, my Rx, or sorry, if I have a point load like this, then I do sum of forces about R, or sum of forces in the y direction. Ry, let's call this 1. Ry equals -1, and our AB, AD, CAD equals 0. So right away I already know all the values when I have a unit load at this point. It's just like what we did for beams. When we have a unit load at this point, the reaction or the shear at any other point on this is going to be 0. So we know that, so that's our first set of points. I'm gonna go through this for the first 2 steps, and I think once I do that, the pattern should be clear on how to do the rest. So that's our first problem. We just do the same thing again. Notice that I don't need to change the location of my cuts. Or I just keep everything the same. There's a handy little trick to remember the force, the reaction here. The reaction is the ratio of these 2 lengths, of this length and of this length. So if you count out how many lengths there are here, there's 1, 2, 3, 4, 5, 6 lengths. If I have a unit load here, the force in the reaction here is going to be 5/6. And I'll let you prove that one for yourself, but so I'll just try out and draw on this. If I have a unit load here, and this is going to be of 1, this is going to be 5/6. If I have a unit load over here of 1, this is going to be 4/6. If I have a unit load here of 1, this is going to be 3/6. And likewise, this is going to be 1/6, 2/6, 3 over 6. You don't actually need to worry about this side though. You just need to worry about what happens here. So this is just a little trick to remember. It'll become very useful later on because it'll save you like a quarter of your equations. So you AB, AD, CD. This is point A, C, and I'm not going to draw points B and D. You just need to, I think the easiest way of solving this one would just be to take moment about A first. And if you do that, you get 5 over 6 times 6 minus 1 times 3 minus CD times 4. Your CD is going to be equal to 1/2. If you do sum of forces in the y direction, you're going to get 5 over 6 minus 1 minus 4/5 AD equals 0. And from this, you're going to get AD equals negative 5 over 24. And finally, if you do sum of forces in the fx direction, you're going to get AB plus CD plus AD times 3/5 equals 0. And then from this, you're going to get AB equals negative 0.375. Just very quickly to show you what changes, I'm going to try and keep this on one page, but I'm almost positive I'm going to run out of space here. If I move I'm just going to move the unit load over one more time. Move it over here. This is going to be 1. So 4 over 6. And my moment equation is going to be, if I take moment about the same point, I'm going to get 4 over 6 times 6 minus 1 times 0 minus CD times 4. Notice how these two equations are exactly the same. All I changed were the force and the distance. So I have a 0 instead of a 3, and I have a 5 over 6 instead of a 4 over 6. Equals 0. Equals 1. And then my sum of forces in the y direction is going to be very similar. Minus 1 minus 4/5 AD equals 0. AD equals negative 5 over 12. Or equals negative 10 over 24, however you want to look at it. If you use it this way, notice that my AD is exactly twice what I had before. My CD is exactly twice what I had before. And now you can kind of guess what AB is going to be. Sorry, I messed this up. This is AB plus CD plus AD times 3 over 5 equals negative 3/4. Okay, so that's pretty much everything. When you're going to the next portion, I won't solve this, but keep in mind that your load your point load does not have to be on the section that you're analyzing. It can be completely off the section. In other words, if you do notice how this point is not on the load. This would be point, I didn't draw this to scale, but this would be point D. My point D is not on my section, but I can still include it on my thing, and I don't have to change my cuts anywhere. I can use the same exact equations that I was doing, just adjust the forces and distances, and that should be fine. I believe you should get the right answer. I will leave it up to some of you to figure out if this gives you a different answer. Yes, I'm a little lazy to figure this out myself. But yes, so you have these values. And then the next question is, what do you do with these values? All you have to do is graph them. Sorry, what am I doing? This is x. So let's call this AB. I already found that my force, that when my force is at the reaction, AB is going to be 0. So I just mark a little 0 point. When my force is at the next point, when I move my force over by one bay, we call each of these things, well, bay is not a good word. There are names for each one of these sections. You go from here to here to here to here to here. The force in AB is going to be negative 0.375. So I just graph that here. And then when I go to the next point, my AB is going to be negative 3/4. Negative 3/4 is 0.375 times 2. So I'm just doubling and going over by over and double. And then I just connect the dots later. So each time you make a new section, each time you move your point load, you're going to get 3 new values, one for each AB, AD, and CD. You are then going to just plot those points on a graph. So I'm going to have 3 charts here. This is AD. AD is going to be, it's going to be just like the last one, but shallower. And then where the CD is going to be positive. So you have all these values. You're just gonna plot them, and yeah, that's pretty much it. So I know this is a little bit short notice, and you guys have I think it's an environmental test tomorrow. But yeah, let us know if you have any questions. I'll send out an email explaining or letting you guys know my office hours for tomorrow. But yeah, anyway, let us know if you have any questions.